Welcome to Course 4, Module 4, Chapter 12, AI and Automation in Circular Supply Chain Decisions. This presentation explains how artificial intelligence, machine learning, optimization, robotics, and digital platforms are changing the way circular supply chains are planned and controlled. The key idea is that circular operations cannot rely only on manual forecasting, because returns, product condition, carbon constraints, and manufacturing demand all change continuously. The chapter therefore treats AI not simply as a technology for efficiency, but as an enabler of autonomous and data-driven decisions. Across the slides, we will move from general AI capabilities to reverse logistics routing, dynamic vehicle routing, remanufacturing yield, supply coordination, sorting, grading, and 3 industry cases that connect theory with practice. Use this slide as a bridge from the previous idea to the next operational decision. In this chapter, we will examine the roles and engagement of stakeholders in the circular economy, review key theoretical foundations, and discuss systems thinking approaches. We'll explore institutional theory and legitimacy pressures, network theory and power dynamics, and collaborative governance frameworks. Finally, we'll look at case studies that demonstrate stakeholder collaboration in practice. By the end, you'll understand how these concepts work together to drive circular economy success and be able to answer key questions about stakeholder engagement and collaboration. AI and machine learning shift circular supply chains from manual planning to predictive, automated decisions. They support forecasting, procurement, optimization, risk management, reverse logistics, recovery, recycling, waste reduction, and carbon management. This slide contrasts the traditional planning mode with the emerging circular mode. In the traditional approach, supply chains often depend on manual forecasting cycles and plans that are adjusted only after disruptions occur. Procurement, logistics, production, and inventory may be optimized separately, which limits the ability to manage circular complexity. By contrast, AI and machine learning enable predictive and prescriptive decisions. They can detect disruptions earlier, recommend or automate responses, and support closed-loop planning for returns, carbon, and resource use. The chapter presents this shift as a movement from decision support toward autonomous action. For circular operations, that matters because timing, product condition, and environmental constraints must be coordinated continuously. Here, the presentation links AI capabilities to circular economy objectives. Machine learning supports forecasting of demand, returns, and risk. Reinforcement learning is highlighted in the chapter as relevant for continuous inventory and network decisions. Big data analytics improves disruption detection, response, and recovery. Robotics and computer vision can support sorting, inspection, and grading of returned products. These capabilities are not isolated technical tools. They are connected to resource-optimizing decisions based on circular principles, including reuse, repair, remanufacturing, and recycling. The chapter also notes that AI can work alongside digital architectures such as blockchain to manage reverse material flows, support carbon accounting, and create incentives for circular business models. Use this slide as a bridge from the previous idea to the next operational decision. Carbon-efficient reverse logistics routing is mainly driven by optimization models and meta-heuristics. Environmental goals become routing objectives or constraints across vehicle routing, location routing, and production routing decisions. This slide highlights a crucial point. In reverse logistics routing, carbon is not simply reported after the fact. Instead, it is embedded inside the model architecture. Cost, emissions, fuel use, service windows, vehicle capacity, and network constraints interact within the same decision problem. The chapter discusses green vehicle routing and low-carbon location routing as examples of this integration. Models may include heterogeneous fleets, electric vehicles, time windows, and 2-echelon reverse networks. These features allow decision makers to select routes, fleet mixes, facility locations, and collection structures that balance economic and environmental performance. The wider implication is that sustainable routing requires prescriptive models, not only descriptive carbon measurement. The methods landscape on this slide summarizes the chapter's view of carbon-efficient routing. Vehicle routing problems, location routing problems, and production routing problems all require methods that can handle many constraints at once. Mixed integer programming, nonlinear programming, multi-objective formulations, fuzzy robust models, and meta-heuristics appear frequently in the chapter. These methods are used because reverse logistics decisions must combine pickups, deliveries, transfers, backhauls, service deadlines, uncertain returns, and emissions. Classical machine learning is described as comparatively rare in this specific literature. Therefore, the main takeaway is that carbon-efficient reverse routing is currently more of an optimization and heuristic domain than a prediction-driven domain. This slide explains why heuristics are so important in carbon-efficient reverse routing. The first step is to formulate the problem, often by placing carbon in the objective function or by using emissions as an operational constraint. The second step is to search through possible routes and network choices. For realistic problems, exact methods may become computationally difficult, so large neighborhood search, adaptive heuristics, and other meta-heuristic approaches are used. The third step is to repair or adjust candidate solutions so that time windows, capacity limits, and routing constraints remain feasible. The final step is deployment, where the model produces fleet and route decisions that can reduce fuel use, emissions, and operating cost. Use this slide as a bridge from the previous idea to the next operational decision. Dynamic vehicle routing responds to real-time changes in demand, returns, traffic, and service constraints. It is not faster static planning. New information can continuously reshape the best route solution. This slide illustrates how dynamic vehicle routing changes the planning clock. In a static routing model, a route is designed before execution and then followed unless a major disruption forces manual adjustment. In a dynamic model, new customer demands or return requests arrive while the route is in progress. The system must then decide whether, where, and how to insert those requests into existing tours. This requires online re-optimization under time, capacity, and service constraints. The chapter connects this logic to real operational settings such as e-commerce, grocery delivery, and emergency response. In those contexts, the value of routing intelligence lies in continuous adaptation rather than in a single planned route. The sensing and decision loop shown here summarizes how real-time routing works. First, the system receives demand signals, return requests, vehicle positions, and route state information. Second, it evaluates constraints such as traffic, delivery deadlines, pickup requirements, capacity, and service windows. Third, an optimization or meta-heuristic engine searches for feasible and improved route adjustments. Finally, updated tours are communicated back to the vehicles or dispatch system. Then the loop continues as new data arrives. The chapter links this process to Industry 4.0 approaches to dynamic vehicle routing. The key message is that data, algorithms, and operational execution must be connected in a continuous feedback loop. This slide adds the reverse logistics dimension to dynamic routing. Circular supply chains cannot focus only on outbound deliveries to customers. They must also integrate inbound returns, used products, cores, or recyclable materials. That means vehicles may deliver products and collect returned items within the same or related route structures. The chapter describes integrated forward and reverse logistics vehicle routing problems, which are often solved with mixed integer nonlinear programming and advanced meta-heuristics. In dense urban environments, two-echelon routing and strict deadlines create additional complexity. The main point is that dynamic routing becomes more difficult, but also more valuable, when it coordinates both forward service and reverse recovery flows. Use this slide as a bridge from the previous idea to the next operational decision. Remanufacturing depends on predicting what value can be recovered from returned products. Direct yield prediction is rare, so researchers often forecast return quantity and quality to infer usable material or component value. This slide explains why yield forecasting is different from standard supply forecasting. In a forward supply chain, inbound materials are usually ordered according to specifications. In reverse logistics, returned products arrive with uncertain timing, uncertain quantity, and uncertain condition. Managers need to know how many items will come back, what quality category they will fall into, and how much usable value can actually be recovered. The chapter emphasizes that yield is often not observed directly in advance. Instead, return quantity and quality become proxies for recoverable yield. This distinction matters for remanufacturing, because production planning, disassembly capacity, spare parts recovery, and inventory buffers all depend on the expected usable output from returns. Forecasting approaches on this slide reflect the methods discussed in the chapter. Earlier work used Box-Jenkins transfer functions to connect product returns with previous sales volumes and time lags. Distributed lag models are also important because they can be updated when new operational data arrives. More recent work has applied Bayesian Markov chain Monte Carlo estimation to improve parameter estimation under uncertainty. These methods show that return forecasting often depends on time structure, causal relationships, and continuous updating. The chapter's key insight is that these statistical models do not always predict material yield directly. Instead, they provide better signals about return timing, quantity, and quality, which then support remanufacturing planning. This slide focuses on the planning implications of yield prediction. The process begins with return signals, such as past sales, customer behavior, and observed product condition. These signals support forecasts of quantity and quality. From there, managers estimate usable yield and translate it into production plans. The chapter stresses that prediction is valuable only when it stabilizes decisions. Better yield estimates can inform disassembly schedules, component recovery, raw material substitution, and inventory buffers. They can also reduce mismatch between uncertain secondary inputs and forward manufacturing needs. At the same time, the chapter points out an important research gap. Direct machine learning models for material recovery yield remain less developed than broader return forecasting methods. Use this slide as a bridge from the previous idea to the next operational decision. Closed-loop systems must balance uncertain secondary supply with reliable manufacturing demand. Quantitative models coordinate new production, remanufacturing, returns, inventory, failures, and backlog risk to keep the system resilient. This slide presents the three streams that must be managed simultaneously in a closed-loop system. The first stream is new manufacturing, where products are produced from conventional inputs. The second stream is remanufactured goods, where recovered items or components are restored for use. The third stream is returned cores, which arrive with uncertain volume and condition. The chapter discusses stochastic dynamic control models that adjust production rates across these streams while considering holding costs, backlog costs, machine failures, and repairs. The managerial insight is that circular supply chain planning cannot treat returns as a separate afterthought. It must control several connected inventories and production decisions at the same time. The levers on this slide show how coordination can be achieved. Dynamic buyback prices can influence the volume and quality of returned products by changing the incentive for customers to return used items. Hybrid production rates can balance new manufacturing with remanufacturing output. Inventory buffers can absorb the variability created by uncertain returns, machine failures, and fluctuating demand. Demand synchronization helps reduce mismatch between what the system can recover and what the market requires. The chapter presents these levers through operations research and control models. Together, they show that circular coordination is not passive. It actively shapes both secondary supply and manufacturing response under uncertainty. This slide summarizes the network effect of poor synchronization. When secondary supply, remanufacturing capacity, and customer demand are not aligned, variability can spread across the extended supply chain. The chapter connects this problem to increased inventory variance and the bullwhip effect. A small mismatch downstream may become a larger planning problem upstream, especially when returned product yield is uncertain. Dynamic control models are therefore important because they continuously manage production rates, inventories, and return streams. The goal is to reduce disruptions, prevent excessive backlog, and avoid unnecessary inventory accumulation. In circular operations, synchronization is a stability mechanism, not only an efficiency improvement. Use this slide as a bridge from the previous idea to the next operational decision in the chapter narrative. AI vision and robotics can accelerate inspection, sorting, and routing of heterogeneous returns. The chapter highlights strong potential, but notes limited algorithm-level evidence for automated visual grading in returned inventory. This slide shows how AI vision can convert messy reverse flows into structured decision inputs. The process begins with returns gatekeeping, where mixed goods enter a warehouse or processing facility. Sensor capture then creates visual or other data about the returned item. AI classification uses that information to identify type, condition, or quality category. The routing decision then determines whether the item should be reused, repaired, remanufactured, recycled, or disposed of. The chapter links this pipeline to automated sorting and inspection in intelligent warehouses. The important point is that vision systems do not create circular value by themselves. They create value when classification results are connected to operational decisions. This slide contrasts what the literature emphasizes with what is less documented. On the one hand, studies of smart logistics, Logistics 4.0, and intelligent warehouses frequently highlight collaborative robots, smart counting, monitoring systems, and AI-supported inspection. These technologies are presented as foundational elements of automated supply networks. On the other hand, the chapter notes that detailed evidence for reverse logistics sorting mechanisms is thinner. Specific grading algorithms, measured error rates, and implementation details for returned inventory are not as well developed. For managers, this means AI vision should be treated as a high-potential capability that still requires careful testing, validation, and integration into operational processes. Automated grading classifies returns by quality before processing decisions. It can improve inventory and remanufacturing performance, but evidence on AI grading accuracy and error rates remains limited. This slide explains why quality categories matter. Without grading, returns are treated as if they were uniform, even though their condition may vary widely. With grading, returns can be separated into quality streams that support different operational decisions. High-quality items may be reused or remanufactured more easily, while lower-quality items may require repair, parts recovery, recycling, or disposal. The chapter cites work showing that quality grading can improve inventory performance compared with systems that do not use grading. Yet the benefit depends heavily on classification accuracy. If the grading system makes many mistakes, the operational and financial gains may be greatly reduced. Automated grading therefore combines information value with error risk. This framing helps the audience connect the visual structure with the chapter argument. The quality paradox captures a central tension in reverse logistics grading. On one side, more detailed quality information helps managers plan remanufacturing, recovery, and inventory decisions. On the other side, the inflow of lower quality returns can create operational burdens, especially if the system misclassifies items. The chapter notes that imperfect grading can sharply reduce the expected profit uplift from using grading at all. This is why classification accuracy is not a technical detail. It determines whether grading actually pays off. AI vision may reduce misclassification, but only if it is trained, validated, and integrated into decision processes that recognize the economic cost of errors. The empirical cases show circular AI in practice. TOMRA for sorting, Cashify for pricing and condition assessment, and Moraloop for matching intermittent secondary supply with demand. This slide compares the three cases and their roles in the chapter. Tomra illustrates how AI vision and sensor-based sorting can reduce misclassification in reverse material streams. Cashify illustrates how condition assessment and AI-powered pricing can influence the volume and quality of used smartphones entering a refurbishment system. Moraloop illustrates how a digital platform can match surplus textile materials with business demand. The shared pattern is that each case addresses a different uncertainty in circular operations. One uncertainty is whether returned items are classified correctly. Another is how much secondary supply will be acquired and in what condition. A third is whether unpredictable surplus materials can be matched to buyers. Use this slide as a bridge from the previous idea to the next operational decision. The Tomra case operationalizes the chapter's discussion of visual grading and misclassification. In deposit return systems, end-of-life beverage containers are returned through reverse vending and sorting infrastructure. Sensors and computer vision can identify accepted materials and route them into validated streams. The chapter connects this to the economic problem of imperfect classification in reverse logistics. If returned items are wrongly classified, the value of grading and sorting can fall sharply. Tomra therefore serves as an empirical example of how sensor-based infrastructure and convolutional neural network style recognition can support circular operations. The broader lesson is that AI vision becomes valuable when it reduces error in material recovery processes. This framing helps the audience connect the visual structure with the chapter argument. The Cashify case connects returned product condition, pricing, and secondary supply control. Cashify operates in the used smartphone market, where product condition strongly affects recoverable value. The chapter describes an AI-powered pricing process that assesses customer-reported conditions such as battery health or structural damage. This assessment supports a dynamic buyback price. That price is more than a transaction value. It acts as a control lever that shapes the volume and quality of smartphones entering the refurbishment system. The case therefore illustrates how circular supply chains can actively manage uncertain secondary supply instead of waiting passively for returns. Pricing becomes part of the operational control system. The Moraloop case focuses on textile surplus and demand matching. The chapter explains that surplus fabrics and deadstock create unpredictable secondary supply streams. These materials may be high quality, but they are difficult to forecast and coordinate with buyers using standard planning approaches. Moraloop addresses this problem through a digital matching platform that catalogs surplus materials and connects them with business-to-business demand. This reduces the friction between intermittent supply and downstream need. In the language of the chapter, Moraloop helps synchronize secondary supply with manufacturing or purchasing demand. The case shows that circular automation is not always about robotics. It can also be about information architecture and market coordination. To conclude, this chapter shows that AI and automation are becoming essential enablers of circular supply chain decisions. They help organizations move beyond static planning toward faster, data-driven, and more adaptive decision-making. In reverse logistics, optimization models can reduce carbon impact while still maintaining service performance. Real-time routing improves resilience by allowing supply chains to react to new demands, returns, and disruptions as they happen. Forecasting also plays an important role by aligning uncertain product returns with production needs. Finally, automation through robotics, AI vision, and grading systems helps transform returned products into valuable resources. Overall, the key message is that circular supply chains depend not only on sustainability goals, but also on intelligent coordination, accurate information, and operational execution. Thank you for your attention. Next, we continue with Module 5, Chapter 13.